So for the problem suggested that's on page 561, number 48, turns out what we have here is a baseball diamond. So let's draw a baseball diamond. And this is 60 feet on a side and 60 feet, and the distance from home plate to the pitcher's mound is 46 feet, and the measure of this angle is 45 degrees, half of 90 degrees, and our first task is to find the distance from home plate, or excuse me, from the pitcher's mound to first base. And we'll just call that C, little c. So C equals, and this is question A, C equals the square root of the length of the two sides, 46 squared plus 60 squared minus 2 times 46 times 60 and times the cosine of 45 degrees. And I came up with C equaling, when I ran that through the calculator, 42.58 degrees. So for B, the question was, how far is it from the pitching mound to second base? Well, we know this for any time you have a triangle 45, 45, 90, and this length of this side's A and the length of this side's A, it's right triangle. We already know from the Pythagorean theorem that the length of the hypotenuse is A root 2. So then the distance from home plate to second base is, and I'm going to call, let's see, we'll talk about distance. The total distance is 60 root 2. But from that, we're going to subtract the 46 feet it takes to get to the pitcher's mound, minus 46 feet. What we have left over is will be the distance from the home plate to second base. And when we compute this, we get 38.85 feet. Now, finally, C, it says, what angle do we have if you're the pitcher and you're facing home plate? Through what angle do you have to turn in order to be facing first base? So let's use the law of cosines again, and we know now we know the measure of this side, the measure of this side. We need to find the measure of this angle right here, and we know the measure of the side opposite. So we'll call this angle, for example, let's just call it A. So A equals the inverse cosine of the square of 46, so 46 squared, plus the square of 42.58, minus the square of 60, the side opposite, all over 2 times 46 times 42.58. And when I computed that, I came up with an angle of 85.2 degrees. So good, we've got the 3 questions answered. Well, now we're doing question 4, which happens to be problem 55 on page 562. And in that problem, they ask us to show that, well, let me draw the picture. We're given a circle of radius r and angle theta, and the distance between these 2 points where the radius connects with the circle is called d. The distance between these 2 points, and r and r, the radius, the length of each of those rays. And so they want us to prove, given that d equals 2r sine of theta over 2. Well, we're going to do that, but we need this identity, and the identity is this, that sine of theta over 2 equals plus or minus the square root of 1 minus cosine of theta, all divided by 2. So let's keep that in mind. Now let's attack this problem. And so we have that by the law of cosines, that distance d equals the square root of r squared plus r squared plus r squared minus 2 r times r, which is r squared, cosine of theta, which equals, and now we have 2r squareds here, minus 2r squared cosine of theta, which equals, factoring out a 2r squared from each term, we get 1 minus cosine of theta. And I'm going to extend this down. Now, if only we had a 2 in the denominator, well, we can put 1 there as long as we multiply, put another factor of 2 in the numerator. So in other words, we just multiplied by 1 in the form of 2 over 2. Now, so hold on to this. I'm going to have to erase this, and but you can backtrack to this anytime. Let's see, over 2 over 2. And now, what we have is d, we're talking about d equals the square root of 4r squared times 1 minus cosine of theta over 2. Well, let's factor out that 4r squared. When you take the square root of 4r squared, we get 2r, and now we've got the square root of 1 minus cosine of theta over 2, but keep in mind that equates to 2r and sine of theta over 2. Sine of theta over 2. And there, we've done it. Good.